Hello. In this video, we are going to analyze a turbine operating at steady state. Open steady systems such as this turbine are discussed in chapter 4 in your textbook. And I'm assuming you're familiar with what is isentropic efficiency. That's what we are asked to find in part C of the problem. So let's first see what information are supplied. The working fluid is air. We are asked to use the PG model and also see if you use the IG model, how the answer would change. The inlet condition is completely given, including the mass flow rate. And look at the exit. I'm assuming there are two different states, two being the isentropic exit state that will produce the maximum theoretical power, and 3 is the actual exit state with the temperature of 220 degrees Celsius. This is how the states looks on a TS diagram. So the isentropic efficiency will be basically, if you eat a turbine, is the definition is that the external work that will get out of the actual turbine divided by the external work that will get out from the isentropic turbine. So let's go get started, find these two quantities, and there you can find the turbine efficiency and all other desired variables. I've already logged in as a student here. So let's find a suitable test step. Turbine is an open steady system, so we trace system analysis, open steady systems, and follow the generic branch to single flow device and PG model. We launch the app by choosing HTML5 tab. Air is already the default fluid, so we don't have to worry about that. And let's start calculating states. So the pressure is given to be 4 MPa. Temperature is 600 degrees C. And the mass flow rate is 5 kg per second. That completes the calculation of the inlet state. The isentropic state, the pressure is given to us. And of course, entropy equals that of state 1. And mass flow rate doesn't change, m dot 1. Now for state 3, notice that I just want to show you some features. Instead of creating a new state, we can spawn a state by clicking the plus button. In other words, it's exactly a state 2 now, the state 3, but we know state 3 pressure is same as state 2, that's we can leave it alone. Entropy is not equal, and the temperature is given, so we could enter the temperature here. Well, let's do even fancier thing. In the I/O panel, we can declare the exit state. Let's go to the user codes. Click there so that it's clean up the page. So we can declare a variable called T-exit, for instance, equals 220. This is the actual temperature given. This must be in Kelvin, which is the SI units for temperature. So we declare T-exit on the I/O panel. So this is accessible to all other panels. So here we could write temperature equals T-exit. So what's the benefit of that? Instead of typing it in here 220 degrees Celsius, the benefit is that we could later go and change the T-exit, and we don't have to come to the details here and update all calculations. Okay, so now we have all the 3 states calculated. Let's make sure they look reasonable on the TS diagram. 1 to 2 should be vertical, this isentropic state, and 3 should be on the right of it. Entropy is generated in a non-isentropic turbine, so you can see that state 3 is to the right of state 2. So you go to the device panel. The isentropic turbine operates between state 1 and state 2. We load those states. And of course, heat transfer is 0, adiabatic turbine. And now if we click the calculate button, the work W.external has been calculated. This is the maximum possible power output. Device 2 is my actual turbine, state 1 and state 3 to operate between. Again, heat transfer is not a problem, 0. So we found the 2 external works we are looking for. We go to the I/O panel, and suppose we declare a variable called eta turbine equals W dot ext, wait a minute, ext, 2 is my actual output, and w dot ext1 is my ideal output, isentropic output. So therefore, as you can see, the eta turbine is calculated and shown in the output area. 75.6% is my answer for isentropic efficiency. Now, just to show you how parametric study works, suppose we said, wait a minute, the temperature out was not 220 degrees Celsius, but 250 degrees Celsius. So then all we do is update. We click the calculate to make sure T exit has been calculated correctly. Now nothing has happened to the turbine efficiency yet, but if I click on super calculate, what happens, it recalculates everything, and now we can go to the details output. At the very bottom you'll find eta turbine has been updated. It has gone down to 69.68%. So let's go back and set the solution back to what we got. We go back to the user code, and let's say the temperature should be 220 degrees Celsius. Original problem, we calculate, and calculate means it registers the new temperature in this panel. It's a local calculate, and super calculate is like a global calculate. So everything has been updated back again, and you can see we have gotten our original answer back, which should be 75.6%. Now for the what if study. What if we use the IG model? So what we do, we copy Control A, Control C, entire test codes, and we go launch a new window and find the open steady device analysis. Instead of PG model, we launch the IG model. So this is an app that's using IG model. You can see in the name here, IG model. Okay, and then it looks almost identical, except CP and CV, etc. are not material property anymore. Okay, in the I/O panel, you can clean up the I/O panel if you want by clicking this button, and Control V. Essentially, we pasted all the codes back. Well, now if we load, what happens is that the app knows that this is the IG panel code. So you'll notice that the air has been changed to IG model everywhere. And the loading means everything has been done for you. And the final answers, whatever answers you're looking for, are there in every panel, but you can go and check. Eta turbine now has been calculated to be 78.9%. So therefore, using a PG model versus IG model does change the answer slightly, sometimes significantly if the temperature variation is very large. So likewise, you can go and look at every panel how the IG model has affected each answer. Anyway, so you can think of the possibility of different kind of studies, parametric study. Keeping the test code saved somewhere is a nice thing, because you can jumpstart the solution. As a matter of fact, if you go to the hands-on example page, you will find the test codes you'll find for many different problems are already here. All you have to do is to click here, and it will show the test code, and you can jumpstart a solution in this manner.